we've seen that we can transform a relation into Boyce-Codd normal form by splitting tables, so using the table decomposition method. However, starting with an arbitrary set of function dependencies can lead to too many unnecessary splits. So therefore, when transforming a relation into Boyce-Codd normal form, we will follow a particular algorithm that leads to a nice decomposition. To transform a relation into Boyce-Codd normal form, we will use the following synthesis algorithm. The input of this algorithm is a relation R and a set of functional dependencies for R. The first step of this algorithm is to compute a canonical set of functional dependencies F. Recall that in order to compute a canonical set of functional dependencies, we first make the right-hand side singular, then we minimize the left-hand sides, and we remove implied functional dependencies. Once we've done this, once we've computed this canonical set, we maximize the right-hand sides of the functional dependencies. So for every functional dependency, x uniquely determines y, we replace this functional dependency by the functional dependency x uniquely determines the cover of x minus x itself. So we take all the attributes that are uniquely determined by x except for the attributes in x. Next, we start splitting the tables. This is basically what we've done before, the table decomposition method, but now since we are splitting step by step, it might be that the right-hand sides of our function dependencies are only partially or not at all in the relation. So therefore it looks a bit more complicated. We will go through it step by step. So we just start with the table R. And then for every table that we have, and for every functional dependency F, so this is this maximized functional dependencies, we check the following. We check whether the left-hand side of the function dependency is fully contained in the relation Ri. If so, we check whether the left-hand side is a key of the table Ri, so we compute the cover of X, and we check whether Ri is fully contained in this cover. If so, then X is a key for this relation and nothing needs to be done. If not, so if it's not a key, so this Ri is a strict subset of the cover, we check whether the right-hand side of the function dependency overlaps with the relation. So at least one of the attributes in the right-hand side should be also an attribute in this relation Ri. So this intersection of the right-hand side and the relation should be non-empty. And if all these conditions hold, then we split. And we split as follows. We compute the intersection of the right-hand side with the relation Ri. So Z will be all the attributes in the right-hand side that appear in this table. And we then remove this attribute Z from the relation Ri, and we add a new relation that contains the attributes X and these attributes Z. So we create a new table that contains the attributes in the left-hand side and those attributes in the right-hand side that also occur in the relation Ri. Before, in the table decomposition method, this Z was always Y. We've created a new table that contained all the attributes in the left and in the right, but now because we are iterating these decomposition steps, it may happen that the attributes in the right-hand side of the function dependency only partially appear in the relation. So therefore we only take the attributes X and Z, those attributes in the right-hand side that appear in Ri. So let's have a look at an example. We consider a relation R that has attributes A, B, C, D, E. And we have 4 function dependencies. The set AB is the only minimal key with respect to these function dependencies. So the first question is, is this table in Boyce-Codd normal form? Already the first functional dependency, A uniquely determines D, is not implied by a key. The left-hand side contains no key, and it's not trivial. So this table is not in Boyce-Codd normal form. So we have to transform it into Boyce-Codd normal form. The first step is that we take these functional dependencies and we compute a canonical set of functional dependencies. Luckily, this first step has already been done for us. We already have a canonical set of functional dependencies. So we can skip this first step and we can start with step 2. We maximize the right-hand sides of the functional dependencies. From the left-hand side A, we can get D, but also E, because D uniquely determines E. So we get a functional dependency, A uniquely determines D and E. From B, we can get C, we can get D, and from D we can get E. So we will have a functional dependency, B uniquely determines C, D, and E. From D, we can only get E. So this is the set of functional dependencies where we have maximized the right-hand sides. Now we are starting the transformation procedure. We will split off violating functional dependencies one by one. We start with our original relation that we now call R0 here. So we start with the relation containing all of the attributes. And now we check, is there a functional dependency that violates the Boyce-Codd normal form? Our first functional dependency already violates the Boyce-Codd normal form, because the left-hand side does not contain a key of this relation. The cover of A is just ADE and not all of the attributes, and this is not trivial. So we split off this first functional dependency. We use the table decomposition method that we've seen before. So how does this work? We will create a new relation that contains the attributes A, D, and E, because A, D, and E all appear in this relation. So we create a new relation with attributes A, D, and E, and from the relation that we have here, we will remove the right-hand side. We remove D and E. So removing from this relation D and E gives us ABC. This is this relation, and the new relation that we've added is ADE, that is this relation. In a new relation, A is the key. Next, we check whether the normal form of one of these relations is violated by some functional dependency. So let's have a look. We look again at R0 and we see that the Boyce-Codd normal form of R0 is already violated by the second functional dependency. The left-hand side is not the key of this relation. B only determines C in this relation, not A. So it's not implied by a key, and it's also not trivial. So now we need to split with respect to this functional dependency. So what do we need to do? Not all of the attributes appear in this relation. Of this functional dependency, we have attributes B, C, D, E. Only B and C appear in this relation. So we create a new table that contains the attributes B and C. And in this new table, B will be a key. We remove the right-hand side from this table. So we remove only C because only C appears. And this will leave AB in this relation. So for this relation here, we remove C, we get AB. And we've added a new table that contains the attributes of the functional dependency that also appear in this relation, namely BC. We have a new table with BC. And in this step, it was really crucial that one of the attributes in the right appears in this table. So for instance, if we now look at R0, then the left-hand side of this functional dependency still appears here, but none of the attributes in the right. Therefore, this functional dependency no longer violates the normal form of this table. A violation is only occurring if at least one of the attributes in the right is in the table. Okay, so this functional dependency does not violate this table. This functional dependency does not violate this table. DE does not appear. So we are done with R0. Let's have a look at R1. In R1, this functional dependency is applicable, but the left-hand side is a key of this table. So the first functional dependency does not violate this. B uniquely determines CDE. There is no B in this table, so that's no problem. D uniquely determines E. We have D in this table, so the left-hand side is contained in this table. The left-hand side is not a key of this table because D only uniquely determines E and not A, so it does not determine all of the attributes. So the left-hand side is not a key. It's also not a trivial functional dependency, and one of the attributes in the right appears in this table. So we have to split. We have a violation of the normal form and we have to split. So we create a new table containing the attributes DE, and we remove E from the relation R1. So we remove E from R1, leaving only AD, and we create a new table with D and E, where D is the key of the new table. Okay, now let's continue checking. Now R1 is fine with respect to this functional dependency because none of the attributes in the right appears in this table. R2 is not violated by this functional dependency. There's no A. It's not violated by the second functional dependency. The B appears in the table, but B is a key of this table, so that's fine. The third functional dependency does not violate R2 because D does not appear in the table. And the third relation is not violated by the first functional dependency. There's no A. It's not violated by the second because there's no B. There is a D, but the D is a key of the third relation. So also the third functional dependency is fine with respect to this relation. So now we are done. There's nothing more to split. This relation is in Boyce-Codd normal form. However, observe that in the splitting process, one functional dependency got lost. Namely, the functional dependency B uniquely determines D, one of the original functional dependencies, can no longer be expressed in our final result, the Boyce-Codd normal form, because we do not have any table that contains the attributes B and D. Let's practice the transformation to Boyce-Codd normal form. We have a relation with attributes A, B, C, D, E, and we are given a set of functional dependencies. Now, the first step of the transformation to Boyce-Codd normal form is to compute a canonical set of functional dependencies. This first step has already been done for us. We are already given a canonical set of functional dependencies. So let's take this set. Write this up. I will reorder a bit for better readability. Okay. The second step is to maximize the right-hand sides of the functional dependencies. So we maximize the right-hand side of this functional dependency. So we compute the cover of E. What do we get? We get E, we get B, we get also D. Because we have B and D, we also get A via this functional dependency. And AC is not applicable, so this is all. Okay, so on the right hand side we have A, we have B, and we have D. E we don't put because this is already on the left. Okay, this we don't need to do because we've already maximized the right hand side for the left hand side E. We have BD uniquely determines A. Let's maximize the right hand side, so let's see what we get from the cover of BD. We get A, we get B, we get D, and what else do we get? ABD, this is not applicable. AC, these dependencies are not applicable, so we only get ABD, and we only write A on the right hand side because B and D are already on the left. Okay, so this is already maximal. For the AC, clearly we get B and D. What more do we get? If we compute the cover of AC, we get A, B, C, D. From A, B, C, D, what else can we apply? We have BD, we get A we already have. And the first one is not applicable, so we are done. We only have, because we have AC already on the left, we only have BD on the right. Okay. So these are the three functional dependencies with maximized right-hand sides. Good. Now we start with our original relation R, which has attributes A, B, C, D, E, and we are going to check whether one of these functional dependencies violates the normal form. So what functional dependency should we start with? Maybe let's start with BD. Okay, let's start with this functional dependency. BD uniquely determines A. So BD is a subset of this relation. So B and D, the left-hand side, fully is included in this relation. The right-hand side A has an overlap with this relation. Actually, it's also fully included here, but it suffices that there's an intersection with the relation. And BD is not a key of this relation because the cover of BD only is ABD, and ABD are not all the attributes of this relation. This is a non-trivial functional dependency, so it violates the normal form of this table. So we need to split. We remove the right-hand side, A, from the table, and we create a new relation. So we create a relation R2 with the attributes of this functional dependency, where we have to check that we only include those attributes on the right-hand side that also appear in the relation. Here we have only A, and A also appears. So we include B, D, and A. Okay, BDA is a new relation, and we remove the right-hand side A from our table. Good. Now, what functional dependency should we check next? Let's say that we check next our functional dependency in front. E uniquely determines ABD. The left-hand side is included in the relation R. The right-hand side is not fully included, but has an overlap, and that's sufficient. The attribute A does not appear, but B appears, and D appears. So we have a non-empty intersection with the right-hand side. The left-hand side is included. So this functional dependency affects this table. The only question is it a key of this table? E uniquely determines A, B, and D, but it does not uniquely determine C, so it's not a key of this table. So this functional dependency violates normal form, and we need to split. So we create a new table, and now the question is, what attributes do we include in this new table? We include clearly the left-hand side, and we include those attributes on the right-hand side that also appear in the relation that the normal form is violated of. So A we don't include because A does not appear in the relation. B appears and D appears. So we include B and we include D, and we remove the right-hand side from this relation. So we remove B and we remove D. Okay. Now let's continue. Let's check, does this functional dependency violate this relation, the normal form? No, E does not appear here, so the left-hand side does not appear. This is the table that we've just created, so this should not be violated. Let's check. The left-hand side appears, but also the left-hand side is the key of this table. E uniquely determines both B and D. So that's fine. So what remains is to check this functional dependency. We have a left-hand side A and C. Here only C appears. A is not part of this table, so this functional dependency is not affecting this relation. Here we have A, but we don't have C, so it also does not affect this relation. And here we neither have A nor C, so this functional dependency does not violate any of these relations. However, recognize that this functional dependency actually got lost by splitting. So this functional dependency can no longer be expressed in any of the tables, because none of the tables contains A and C together. So this is not a problem. We know that in the transformation to Boyce-Codd normal form, sometimes functional dependencies get lost. Okay, so we have our result. We have our three relations. The first relation with attributes CE, a relation with attributes BDA, and a relation with attributes EBD. And that's our Boyce-Codd normal form. Yeah, our result is correct. This is not the only correct result. Depending on the order in which we consider the functional dependencies, we can get different results, and the system will accept any correct answer.